Well, now the next talk is by Hanci from Hyang Jialong Liverpool University. And the title of the talk is Infinitely Many Non-Collapsed Steady Ricci Solutions on Complex Line Bundles. Please.
Thank you. Доброго дня всім членам конференції. Я Hanci з Сіанського交通Ліверпульського університету у Китаї. Дуже радий знову взяти участь у цій конференції та виступити з доповіддю.
Ой, дуже приємно. Дуже приємно. Дякую. Ми раді бачити.
I'm doing my best. I'm doing my best. Right. So it is my great pleasure to join this online conference to share some recent progress on the constructions of new Ricci solitons. So the title is Infinitely Many Non-Collapsed Steady Ricci Solitons on Complex Line Bundle. So first of all, a little bit of definition. A Riemann metric, we call it a Ricci soliton if this equation is satisfied. That is, the Ricci curvature plus the lead derivatives of the metric along some vector field plus some constant multiply the metric equals 0. And here the capital X is some vector field and epsilon is a constant. And more particularly, if the lead derivative term is the Hessian of some potential function, in that case, we call the Ricci soliton a gradient Ricci soliton. And with different sign of the constant epsilon after normalization, right? If epsilon equals to 1, 0, or -1, then we call the Ricci soliton expanding, steady, or shrinking. So these are the basic definitions. And very naturally, by looking at the equation, we know that a Ricci soliton is a generalization of a Einstein metric, right? So if the potential function is trivial, then you don't have the lead derivative term, then we already have the Einstein equation. And one of the significance of a Ricci soliton is that it automatically gives you a self-similar solutions to the Ricci flow. And on the other hand, the shrinking solitons and steady Ricci solitons, they are candidates for blow-up singularities of the Ricci flow. So I would like to clarify what that means. So if you have a Ricci flow, you're flowing the metric, so we will hit to the flow might hit the singularity at some point. And if we blow up this singularity, it might look like a Ricci soliton, right? And the reason that we call they are candidates is because not all shrinking solitons and steady solitons are the singularity models. We actually require them to be non-collapsed. So here's the next definition. So in order to define what does it mean by a non-collapsed Ricci soliton, we have the definition that is so-called the kappa non-collapsed. So we say a manifold at the point X and at the scale R is kappa non-collapsed if you have a geodesic ball that is centered at X. And once you control the Riemann curvature, the volumes of the geodesic ball divided by the Euclidean volume is larger than or equals to kappa. So if this inequality is satisfied, we say that the manifold is not kappa non-collapsed at the point X with the scale R. And globally, we claim that the manifold is non-collapsed if you can find some kappa that is larger than 0, so that the manifold is kappa non-collapsed everywhere and with respect to any scales. And by the very famous work of Perelman, that is the no local collapsing theorem, only the non-collapsed Ricci solitons can be the blow-up limits for the Ricci flow. And in our talks today, we're going to focus on the steady Ricci soliton. So we will list out some examples of collapse and non-collapse Ricci solitons, steady Ricci solitons. So for the non-collapse case, if you're talking about Ricci flat metric, that is when the matrix tends to a cone at the infinity. So like when the non-compact manifolds, right, infinitely far away, it's getting more and more like a cone based over the metric Gn on the subspace M. And the growth rate is given by t squared. The very famous Ricci flat metric, the Gucci-Hanson metric, or the later generalization by Bergeri, they all have the examples of a AC Ricci flat metric. Also, some of these Ricci flat metrics have special holonomy. For example, the Bryan-Solomon G2 and spin 7 metrics, they are asymptotically conical. And later on, the construction is further generalized by Christoph Bern and Matthias Wink. And in Matthias' work, uh, like he replaced the principal orbit by a complex, well, by various hot vibration, hence giving many different non-collapse Ricci flat metrics, also including non-collapse steady Ricci soliton. That is where when the manifold tends to a paraboloid instead of a cone at the infinity. So as you can see here, the growth rate here is no longer t squared, but t. Right, and the very famous Bryan soliton, Bryan steady soliton, high dimensional version, it is non-collapsed. In fact, it's asymptotically paraboloidal, right? So infinitely far away, it looks like a paraboloid. And also, more recently, in 2017, by the works of Alexander Appleton, he proved the existence of a bunch of non-collapse steady Ricci soliton with the dimension as low as 4, which is quite surprising. Right, and today in our more recent work, we will also have some, asymptotically paraboloidal Ricci soliton. Right, as for the collapse Ricci solitons, for Ricci flat metric, we have the so-called the ALC asymptotic. That is, at the infinity, the subspace looks like a circle bundle over a n-2 dimensional space, where the metric component tends to a constant. So here A is a positive constant. So compared to the AC asymptotic, right, the circle fiber becomes less and less obvious at the infinity. And for previous work, we have, these 4 people, like Zvatic, Gibbons, Liu, and Pope. They have some collapsed Ricci flat metric that is G2 and, well, that is spin 7, right? They have special holonomy. Also, in a more recent work by Matthias Wink and me, we also have many collapsed Ricci flat metric. And also for non-Einstein steady Ricci soliton, we also have this so-called asymptotically cigar paraboloidal. So here you can see at the infinity, the metric components for this fiber, it goes to some constant, while the base space, it has volume growth rates of t instead of t squared. Right. For the Kähler steady Ricci soliton constructed by Cao, Huaidong Cao, and the later generalization by Andrew Dancer and Mackenzie Wang, they all have the examples of collapsed steady Ricci soliton. Right. So these are the non-complete list of some complete collapse and non-collapse Ricci solitons. So as you can see, the equations for a Ricci soliton is quite complicated. It's a set of PDEs. So how can we construct more example? Well, one very effective way is to impose the conditions of cohomogeneity 1. That is, if we have a Lie group acting isometrically on the manifold, so that the principal orbit is of codimension 1. In that way, we can reduce the PDEs to a set of ODEs. So you can treat the cohomogeneity 1 condition or the cohomogeneous one geometry as the next case to the homogeneous space, right? In the homogeneous space, everything becomes algebraic, but for cohomogeneous one, you still have derivative, but that's the derivative with respect to the one-dimensional orbit space. So you have a systems of ODEs instead of PDEs, and we hope in that way we can get some more examples. Right, and to be more specific, for our topics today, we are going to examine the cohomogeneity 1 complex line bundles over CP2M plus 1. So the hypersurface, it actually comes from the total space of the quaternionic Hopf vibration. So you can think of the principal orbit, 4m plus 3-dimensional sphere, modulo the zk, as the collections of all the unit quaternionic vectors in m plus 1 quaternionic vector space. And that way you have a very natural action from the group G. And the isotropic groups of the 0.000 until you have 1 at the end, it will be this group. Okay, and the group action actually descends to the singular orbits. It descends to the CP2M plus 1. And at the same point, at the projections of the point, the isotropic group will be given by H. So in that way, the principal orbit has is actually a total space of the homogeneous vibration, where the fiber is a circle modulo zk. But a circle modulo zk is still a circle, right? So you have this structure. And of course, the hypersurface geometry it depends on the Lie algebra. With respect to the group K, we can decompose the quotients of Lie algebras into 3 components. So the one-dimensional component is controlling the circle fiber, and 2 and 4 they simultaneously controlling the CP2M plus 1. So in our case, the singular orbit can be squashed in some way. Right, and of course, you can also view CP2M plus 1 as the total space of the twistor bundle over HPM. Right, and any invariant metric on the hypersurface Gma K will be look like this. And now we are letting F1, F2, F3 to be single variable function that is defined on the orbit space. So they are defined on T. Right, and of course, we have a initial condition. So when t is larger than 0, you have a hypersurface, high-dimensional hypersurface. And at t equals 0, the hypersurface, the principal orbit collapse to the singular orbits, which is CP2M plus 1. Therefore, we need the circle fiber to collapse. So it is equals to 0 when t equals to 0. And for F2 and F3, we ask them to be some positive number at t equals 0. And of course, H1 does not have to be H2. So if they are equal, the singular orbit is actually Fubini-Studi. But if H1 is larger than H2 or the otherwise, then you don't have a Fubini-Studi CP2M plus 1. Right, and for smooth extension, we need the derivatives for F2 and F3 to be 0. And for F1, its first derivative should be the integer k, not 1, right? Because here the principal orbit that we have is the 4m plus 3-dimensional sphere modulo zk. So if k equals to 1, then of course F1 derivative should be 1. But if k is not 1, that means we are winding around, right? We are taking the circle fiber modulo the zk. So you're rotating k times. So for smooth extension, the first derivative actually needs to be k. And as for the potential function, without loss of generality, we can let it to be 0 at t equals 0. And the first derivative should be 0 for smooth extension. But later on, we will realize that for second derivative of the potential function at t equals 0, it is actually a free parameter. So we actually have a parameter coming from the second derivatives of the potential function. And so now we can introduce our main result. It consists of two parts. The first part is when K is equals to 1 and 2, that is when the complex bundle is O negative 1 or O negative 2, there's a continuous two parameter families of complete steady Ricci soliton controlled by two parameter. So theta here is controlling how the CP2n plus 1 is squashed. And as the function S, it comes from the second derivatives of the potential function. Right, so here you can see if I let S to be 0, then I have Ricci flat metric. And because K equals 1 and 2, they are all collapsed. Okay, and when S is larger than 0, then all the steady Ricci soliton, they are also collapsed for K equals to 1 and 2. And so here I'm only discussing the case where theta is between 0 and pi. When theta equals to 0, then the singular orbit is not squashed. So we actually go recover the study by the Alexander Appleton. So here I would like to list out the new examples. So here I'm letting theta to be between 0 and pi. As for the meaning where theta hits pi, I'll talk about it later. Right. So anyway, for this case, they're all collapsed, and the lower dimensional space is non-Kähler at the infinity. So like for the homogeneous space, either you have a Fubini-Studi CP2n plus 1, or you have the non-scalar, non-standard homogeneous CP2n plus 1. Right, but things become very complicated in the situation where K is larger than or equals to 3. Right, for this case, we are not able to give a definite tell about the non-collapse Ricci soliton. In particular, all we can say is that there will be some non-negative number, alpha k theta, with respect to any choice of theta and k, such that, well, if the S is smaller than this constant, then you have a complete steady Ricci soliton. And when S is rigorously less than the alpha, then you have the collapsed Ricci soliton. And when S equals to the alpha, then either you have a non-collapsed Ricci flat metric, or you have a non-collapsed Ricci soliton. And it depends on the specific value for alpha k theta. And for our research, we did not figure out like what's the formulas of alpha in terms of k and theta, but we know that it's there. So this is a existence statement. And we realize that for all these non-collapsed Ricci soliton, the base of the cone or the paraboloid is the non-standard 4n plus 3 dimensional sphere. So it's the Jensen sphere. Right, so let's give a closer look to the dynamical system by the Aschenberg and Wang. We have a very systematic way to reduce the PDEs to the dynamical system. So this is the ODE system, right? So if you look at it, the left-hand side of the equality sign, it is the derivative of the principal curvature, and the right-hand side, the first derivative term here, this is the generalized mean curvature. So the capital L is the first fundamental forms of the hypersurface. And here you have a first derivatives of the potential. Right, and as for Ri, so this is the intrinsic Ricci tensor of the principal orbit. So these terms, they don't have derivative. You have a bunch of rational functions. And also we have some kinds of conservation law for the second derivatives of the metric component and the potential function. Right, and Rs here, this is the scalar curvatures of the hypersurface. Right, so how can we deal with this? So it looks rather complicated. It's a second order ODE systems. And we know that F1 has to collapse to 0 at t equals to 0. So you have some kinds of singularity going on for this dynamical system. So we need to find a way to compactify it. And well, before talking about that, by Richard Hamilton, we know that there's a conservation law in terms of the potential function. So we have some kinds of constants such that this is equality is always true. So this is the cohomogeneity one version of the conservation laws by Hamilton. And if I cancel out the second order derivatives of the potential function using this equation here, then I have the conservation law to be written in terms of first derivative, right? And by Binlong Chen, we know that for Ricci soliton, for steady Ricci soliton, C has to be less than or equal to 0. And in particular, if C equals 0, you have a Ricci flat metric. And this conservation law will be useful in our later work. Right. Speaking of the compactifying the dynamical system, we apply the coordinate change that is first developed by Thomas Ivey back in 2094. And it is later used by Andrew Dancer and Mackenzie Wong to construct many examples. We normalize the one-dimensional orbit space using the generalized mean curvature. And then we consider the following functions. So here xi, you can think of it as the principal curvature in some sense, right, with normalization. And Z1, Z2, Z3, Z4, they are just metric component after normalizations. And the function g here, this is just the squares of the trace of the squares of the first fundamental form. And h here is the classical mean curvature, right? If you think of the definitions for xi, so that is what h is. But of course, by the definitions for xi, you can also think of h as the first derivatives of the potential function. So if h equals to 1, then it means that u prime equals to 0, right? So the Einstein case is actually characterized by having h equals to 1. Right, with this coordinate change, if I'm letting prime instead of dot to be the derivative with respect to eta, then we have the dynamical system reduced to a first order polynomial flow. So one of the advantage of this new system is that the right-hand side, they are all polynomial. And the initial condition is reduced to a critical point. And here the Ricci curvatures, they becomes polynomials, including the scalar curvature. And the Q here, it is just the conservation law that we have just mentioned. Right? So if I use the coordinate change, then I realize that Q has to be less than or equal to 0. So the Ricci flat system is characterized by Q equals 0 and H equals to 1. So that is why we have this subsystem, right? You have a steady Ricci soliton system, and you have a subspace, which is you intersect the original phase space by these two algebraic surfaces, and you have a subspace, a subsystem. Also, you can let Z2 to be Z3 and X2 equals to X3. So if you look at the derivatives of Z2 and Z3, oh, sorry, X2 and X3, right? We need to equate R2 and R3. While if you have R2 equals to R3, indeed, Z2 equals to Z3 can satisfy that, right? So indeed, this is a subsystem. This is an invariant subset, and a subsystem on it will be representing the Fubini-Studi CP2n plus 1. So the subsystem here give you a non-squashed singular orbit. And finally, for R3, if we have x equals to Z3 equals to 0, this is also a invariant subset. And the subsystem defined on it actually give you a degenerate case. Why? Because, well, if Z3 equals to 0, R3 is 0, X3 is also 0, but here, equivalently, it means that you're having the letter M to be 0. So this is a four-dimensional system, four-dimensional cohomogeneity 1 Ricci soliton system. like hidden in this higher dimensional, dynamical system. So this is a degenerate case, right? It's degenerating from the higher dimensional case to the four-dimensional case. And this is also a key observation in our work. Like I said, right, using this coordinate change, the initial condition, it got reduced to a critical point by, figuring out the Jacobian. Immediately, we have a 3-parameter families of local solutions, including the K. So one thing that we need to emphasize is that no matter what K is, right, no matter what the topologies of the space is, you have the same dynamical system, right? That means that you are not able to tell the difference of the geometry at the neighborhood around the principal orbit, right? The only neighborhood that you can tell the difference is, the neighborhood around the singular orbit, where the initial condition occurs, right? So therefore, we tend to fix the letter K, right? So once we have K's to be fixed, it means that the geometry, the topologies of the complex bundle is fixed. And for each K, you have a 2-parameter families of local solutions around the singular orbit. Right, like I said, for S equals 0, you have Ricci flat metric. And for S, right, for theta is not 0, oh, sorry, for theta is to be 0, then you have a non-squashed singular orbit. And when theta hits the limit pi, then the metric degenerates to a 4-dimensional Ricci soliton, right? So now let's talk about the proof. Right? We are able to prove the first theorem quite easily. It turns out that for k equals to 1 and 2, we can simply just construct the following set. Right? We define a function that looks like this, and this set, script f, it is invariant and it is compact, right? So in order to check that it is invariant, you simply just take the derivatives of these, functions, and then it turns out that the derivatives of these functions will be written in terms of the other functions that appears in this definitions. So indeed, this is an invariant set and it is compact. So immediately we are able to prove that all these integral curves, they stays in this compact invariant set initially. Therefore, they are defined on the real line. Therefore, the completeness is immediate. But things become very tricky when k is larger than or equals to 3. It turns out that if this inequality is true, the function f2 is larger than or equals to 0 is not satisfied initially. That is, all these integral curves at the very beginning, they're not in the script f. So that caused a lot of trouble. So we will use some other ways to investigate this case. Right, and the way that we do it, well, notice that for this picture, right, this is just the projections of the whole phase space. And we divide the phase space into 3 parts for k to be larger than or equal to 3. So you have the green part that is given by, these two inequality. So script c is invariant, but it is not compact. So if integral curves enter this set, it means that the metric that the curves represent, it degenerates eventually. So this is more or less a very bad set. And the script A is a good set, right? So its definition is here. If the integral curve enters the set script A, it means that, well, because it's compact and invariant, then the integral curves, they are defined on the real line, so the completeness immediately is true, right? And at the between the set A and set C, we have the set B. So this set is compact, but it is not invariant because the integral curves can enter the set A in this way. So that's our initial analysis. And we realized that we can generalize the work done by Matthias Wink back in 2017. In his work, he analyze the situation, the possible asymptotic for Ricci solitons, where the principal orbit comes from a two-solent Hopf vibration, right? But for our case, the Hopf vibration has 3 isotropy solent. And it turns out that in the generalization, we realize that there are only 4 possible asymptotic for complete Ricci solitons, represented by integral curves that is either stays in the set B or enters the set A eventually. So here, well, if it enters set A, then it means that we have collapsed Ricci soliton, and the base of the asymptotic cone or paraboloid is always the non-Kähler CP2n plus 1 if the theta is not 0, right? That is if the singular orbit is not squashed. On the other hand, if you have a integral curve to be staying in the set B, then congratulations, you have a non-collapsed Ricci soliton, right? And depends on whether the CP2n plus 1 is squashed or not, right? You either have a standard sphere or a Jensen sphere as your base, right? And of course, if the integral curve enters set C, then that's a bad news, right? The metric degenerates. Right, and the other key lemma that we're going to use is the generalizations of the Appleton's lemma. So by the works of Alexander Appleton, we realize that no matter what theta is, right, if you have some integral curves that enter the very bad set C, we can increase the parameter S. That is, we can decrease the second derivatives of the potential function, right? So that it is much enough so that you can drag the integral curves so that it will enter the set A eventually, right? So in that way, you have a critical situation, right, where the integral curves that it stays in the set B. So in that way, we can prove the existence of non-collapsed Ricci solitons. So that's the key lemma for by Alexander Appleton. He showed that when theta equals 0, this can be done. And we show that, well, if theta is larger than 0, this is also doable. You can still, drag the integral curves so that it enters a set A eventually by increasing the parameter S. Right, a little bit of picture, like a little review. So if k equals 1, right? So this is a higher dimension picture, right? So the yellow part is the set F that we have constructed. So here I'm showing you like these red dots, they are intersection between the integral curves where the parameter S equals 0 and the wall given by the set A, right? So they eventually hits the wall and enters the set A eventually, right? So like they all come like these red dots, it comes from Ricci flat metric, integral curves of Ricci flat metric. So they all collapse, right? And for k equals to 2, once again, for the Ricci flat metric, they all hits the wall, from the set A, so they are all collapsed, except when theta equals to pi, the degenerate case, you have the 4-dimensional non-collapsed Ricci flat metric, which is the Eguchi-Hansen metric, right? So our result recover this metric. It is all consistent. And things become funny when k is between 3 and 2n plus 1. This time, if you're thinking about the integral curves of Ricci flat metrics, some of them will go to the bad set C, and some of them will go to the good set A. So you have collapsed Ricci flat metric by our earlier work on the Einstein metric. But also, Appleton, he shows that, for 4-dimensional case, for the critical case where pi equals to pi, right? This integral curve, it will enter C. Therefore, by continuity argument, we show the existence of an integral curve that stays in the set B. And for this integral curve, the theta here is not 0, it's not pi. Therefore, it has the asymptotic that is based over a Jensen sphere. All right, so that's the interesting part. And for the non-Einstein Ricci soliton, we use the generalizations of Appleton's lemma. so that you have a some large enough constant alpha such that for any theta, these integral curves will go to the set A eventually. So this blue line here, it comes from the intersections for all these integral curves and the wall given by A, right? And so these integral curves, they're all collapsed. And by continuity argument, right, if I consider, let's say for this point and this point here, then I'll have a new integral curves that stay in set B, right? And you can do this by many, many points, therefore generating many, many non-collapsed Ricci solitons, right? And geometrically, they're all different, which is great, right? And in particular, right, when theta equals to 0, you have the Appleton's non-collapsed Ricci solitons. And the things become similar for k equals to 2n plus 2, and this time you only have one non-collapsed, Ricci flat matrix, and all the other integral curves that goes to the set C. That's bad, right? But it's fine for the non-Einstein steady Ricci soliton, because the generalizations for Appleton's lemma still work, and we can apply the continuity argument again, therefore generating many, many integral curves that stays in the set B. Right, and finally, for the case to be so large that is larger than or equal to 2n plus 3, all these Ricci flat integral curves that goes to the bad set C. But nevertheless, right, the generalizations for Appleton's lemma still works, right? And you can, by the continuity argument, still infinitely many non-collapsed steady Ricci solitons. So that rounds up my my work. Yeah, дякую за увагу. Thank you. Thank you very much.
Thank you very much. Thank you. Let's send the speaker. Thank you.